Hello everyone, I am Darshan A, Assistant Professor of Mathematics. In the previous sessions, you have learnt about isomorphisms. In this session, we are going to learn about theorems on isomorphisms. Theorems on isomorphism. Consider the first theorem. If F is an isomorphism from a group G onto a group G dash, then f of E is equal to A dash, f of A inverse is equal to f of A whole inverse for all A belongs to G, f of A power n is equal to f of A whole to the power of n for all A belongs to G and n belongs to Z, where E dash are the identity elements of group G and group G dash respectively. If you remember, the same theorem we have proved in case of homomorphism. The same proof can be done here as well. If you have not watched that video, you can find the link of that video in the description. Let us consider the next theorem. Suppose if F is an isomorphism from a group G onto a group G dash, F inverse is an isomorphism from G dash onto G. G is abelian if and only if G dash is abelian. G is cyclic if and only if G dash is cyclic. If H is a subgroup of G, then f of H is a subgroup of G dash. First, we shall show that F inverse is an isomorphism from G dash onto G. Let us consider xy belongs to G dash. Since F is onto, there exist elements AB in group G such that f of A is equal to x and f of B is equal to y. And this implies f inverse of x equal to A and f inverse of y is equal to B. And now consider f inverse of x into y, where x is f of A and y is f of B. This will be equal to f inverse of f of A into f of B. But since f is a homomorphism, this can be written as f of AB. So this is equal to f inverse of f of AB. If we cancel f inverse and f, we get AB, where A is f inverse of x and B is f inverse of y. We have shown that f inverse of x into y is equal to f inverse of x into f inverse of y. Since x and y are arbitrary, this is true for all x, y belongs to G dash. Hence, f inverse is a group homomorphism. Let me take this statement as 1. Next, since f is both 1, 1 and onto, f inverse is also both 1, 1 and onto. Let us consider this as 2. From 1 and 2, f inverse is an isomorphism from G dash onto. So this completes the proof of 1. Next, we shall show that G is abelian if and only if G dash is abelian. I just give the outline of the proof. If G is abelian, if and only if AB is equal to BA for all AB belongs to G. Since f is an isomorphism, f is an 1-1 function, and therefore we can write f of AB is equal to f of BA for all A comma B belongs to. But since f is a homomorphism, this can be written as f of A into f of B is equal to f of B into f of A for all A comma B belongs to. Now the elements of G dash are of the form f of A, where A is an element of G. Since f is onto, every element can be written in this form. So these two elements represents arbitrary elements of G dash. So I can write xy is equal to yx for all x comma y belongs to J dash, where x is f of a and y is f of b. And this completes the proof of 2. Next we shall show that G is cyclic if and only if J dash is cyclic. In case of homomorphism, we have shown that if H is a cyclic subgroup of G, then f of H will be a cyclic subgroup of J dash. Here G is a subgroup of G itself, so since G is cyclic, f of G is also cyclic. But since f is an onto function, f of G is nothing but J dash. J dash is cyclic. And conversely, since f inverse is an isomorphism from J dash onto G, the same argument in terms of f inverse proves that if J dash is cyclic, G is also cyclic. And finally, we shall show that if H is a subgroup of G, then f of H is a subgroup of J dash. This follows from the fact that f is a homomorphism. Consider the next theorem. The relation isomorphism on the set of all groups is an equivalence relation. We denote group G is isomorphic to group J dash by this symbol, read as G isomorphic to J dash. To show that this relation is an equivalence relation, we have to prove 3 conditions. The first condition is the relation is reflexive. Next, we have to show that the relation is symmetric. And finally, we have to show that the relation is transitive. First, we shall show that the relation isomorphism is a reflexive relation. For any group G, we can define a mapping f from G to G dash by f of x equal to x, which is the identity map. Then this map is clearly a homomorphism and 1-1 function as well as onto function. And hence, the relation isomorphism is a reflexive relation. G is isomorphic to G for all groups. Next, to show that the relation isomorphism is a symmetric relation, suppose if G is isomorphic to a group G dash, then there exists a mapping f from G to G dash such that f is an isomorphism. We have already shown that if f is an isomorphism, f inverse from G dash to G is also an isomorphism. So G dash is isomorphic to. This proves that the isomorphism is a symmetric relation. And finally, we shall show that the relation isomorphism is a transitive relation. Suppose if G is isomorphic to G dash and G dash is isomorphic to G double dash, then there exist mappings f from G to G dash and G from G dash to G double dash such that f and G are isomorphism. To show that G is isomorphic to G double dash, we define the composition of G and F, G of F from G to G double dash. Clearly, since f and G are 1-1 and onto, G of F being the composition of G and F is 1-1 and onto. Now we show that this mapping is a homomorphism. Consider AB belongs to G and G of F of AB. This is nothing but G of F of AB. Since F is a homomorphism, this can be written as G of F of A into F of B. Now G is a homomorphism. This can be written as G of F of A into G of F of B. And this is equal to G of F of A into G of F of B. And this shows that G of f is a homomorphism, and we have shown that G of f is a homomorphism. G of f is an 1-1 function and onto function, and hence G of f is an isomorphism, and this shows that G is isomorphic to G double dash, and this completes the proof of theorem 3.